Hello, everyone, and welcome to this materials-themed show as part of the Resonate Festival, which is part of City of Culture, Coventry. Now, that means there's lots of very exciting events going on around us over the next year or so, and I hope that you can tune in and take part in some of them and get excited about the place that we live in. Now, why would we want to talk about materials? Well, everything around you is made of something, right? Everything that you've ever owned or touched or eaten or built or broken has been made of something, some material. And it's important that we make the right choices and make things out of the right materials so that the things work, for one, but also that we can make them again in the future, that they're sustainable, and that we have a healthy planet for us all to live in. So obviously, I can't be there with you in the classroom right now. I wish I was. I wish I could give you all a big wave. I hope you're all waving back right now. But I can't. I can't be there with you. So what I want to do instead, I want you to ask your teacher what they want you to do. Do they want you to put hands up? Do they want you to shout out? Do they want you to write something down? Or do they want you to turn to someone next to you and tell them the answer to any questions? So when I ask a question, I'm going to give you a big 10-second countdown, and I want you to do whatever your teacher asks you to do. Does that make sense? So teachers, tell your class now, do you want hands up, shout out, turn to the person next to them, or write something down? Okay, cool. So here's the first question. What I want you to do is think right now, what material could you touch? What can you reach? What could you grab? And what words could you use to describe that material? So ready? I want you to reach out and touch a material right now. So touch a material and then think about the words that you could describe it. And then you've got 10 seconds, whatever your teacher said, however they want you to answer it, 10 seconds to describe that material. So go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And that's time up. Teachers, how did they do? Give them a big clap, thumbs up if they answered really well. It can be quite confusing. I bet some of you have touched a desk. We've all got one of those in front of us at the moment. Maybe some of you were thinking about the glass that goes in the screen or in my webcam. But maybe some of you were thinking about something else. Now, what if I said to you, touch a flexible material, touch a material you can bend? Okay, so another quick example for you. Pick a material and touch a material that you could bend right now. Is that easy? Is that difficult? Well, hopefully you've all picked something like your jumper. That can be bent, it's flexible, it's a bit stretchy, you can move it. What about something really hard, really solid? That's again maybe the desk. We could think about something else. What about maybe your teeth? They're very hard as well. So there's a lot of materials around us, and there's a lot of different words that we could use to describe them all. So what I can do is I can show you loads of those words. So don't worry, I'm not expecting anyone to learn all of this. I'm not expecting you to remember any of these, but think about how you could test for some of these properties. What could you do to try and find out whether a material is hard? How could you find out if a material is strong? How could you find out whether a property exists in that material? So is it magnetic? Does it conduct? Can I stretch it? Can I snap it? Can I squish it? Can I squash it? Can I bend it? Can I break it? You can think about all of those things. And that's what we're going to do in this session, is look at how we can experiment with and test materials and see how they behave. So like I said, I'm not expecting anyone to learn all of those boring words, but we might use some of them as this session goes on. Now, I've got a big old box of materials, and there's lots of things that we could start to think about. What are the first words that you might think of when you were trying to describe a material? So if I picked up, let's say, for example, I've got a bit of metal. Okay, you can hear it, solid bit of metal. So again, I'm going to give you 10 seconds. Remember, however your teacher asked you to do this, whether it's shout out, hands up, turn to the person next to you, or write it down, what words would you just use to describe a piece of metal? So whenever you're ready, off you go. 10 seconds again. Three, two, one. Okay. Now, I'm guessing a lot of people have used words like strong or hard or heavy. It's definitely heavier than, say, a piece of paper. But also, if I hold it like this, it's not bending, is it? It's not floppy. So it's quite a stiff material. That's the technical word that we would use, is stiffness. But can we make metal bendy? Have you ever seen a bendy piece of metal? Well, I've got a good example. How about a great big ruler? Now, you don't normally expect metal to be floppy, do you? But this is certainly a very bendy ruler. But if I turn it this way, it's a little bit, if I can hold it still, if I hold it this way, it actually won't bend in the same way. It'll hold its shape. That way, floppy. That way, it's quite stiff, it's quite strong. So there's a lot of things we can do with these materials. If you wanted to think about a material that was definitely very floppy, what about a piece of paper? So I've got a piece of paper here. If I hold it like that, it flops down, right? Floppy. What if I hold it like that? Now it's holding its shape. So now it's quite a stiff material. How does that happen? How do we change the properties of a material without even really trying? I mean, a classic way of doing that is if you fold a piece of paper. So this guy is folded into lots of triangles. So that will hold its shape, but it's also really strong. So if I try and squish this, I'm actually trying quite hard. I can't squash that. And it's exactly the same if you've ever got a package in corrugated cardboard. Bending it like this, folding it, makes it really quite strong. So if ever you've got to build something out of paper, remember this shape because it'll come in very, very useful. So what else could we look at? We could look at maybe materials that we can squash or bend. So I've got a material here that I can squash. This is a tiny little spring. So that's quite squishy, but it pops back to its original shape. So squish and then it pops. You can do the same thing with something like an elastic band. It's stretchy, and when I let go, it pops back to the original shape. But not all things do that. So for example, if I took a paper clip, I can bend this, I can bend it, but it doesn't pop back. It stays bent. So how come this thing, you can bend it, but it doesn't pop back, it stays where you put it. But this one, that pops back. I can stretch it, let go. So there's a lot of different things that we can play with materials, and that piece of metal bending, it's acting like a bit of Play-Doh or modeling clay, plasticine. I can squash this into whatever shape I like and it will stay there. So sometimes metals will behave like this, like a bit of plasticine. So fancy word alert, it's got plasticity. And sometimes materials will be bouncy and they'll pop back to their original shape, like elastic bands, and that's elasticity. So remember, as I go on, if you've got lots of questions, your teachers can put them in the Q&A section here. We've got a behind the scenes wizard ready to bring the questions over to me, and I'll be able to answer them. So I'm going to ask you now, think about a material that you could reach on your desk that might, what about something that might bounce? How would you find the bounciest material? Is there something that maybe you've got in your pencil case that might bounce? What kind of thing would you look for? So I'll give you 10 seconds to have a little think. How would you find a material that could bounce? I mean, I'm cheating, obviously, I set this up, but I've got a ping pong ball here, and this will definitely bounce, and it will definitely bounce quite high. But I think the best thing that you could probably find in a classroom is going to be something like a rubber, an eraser. So if you found one of those, you've done really well. But what you're looking for is a material that's a little bit squishy, can squash it a bit, but it will pop back to that original shape. Something round, they generally bounce a little bit better than something square. You don't see many square footballs. But I'm going to show you another clever little trick that you can do with these. And the reason I'm going to show you this trick is I want you to remember that there's a lot more going on than just the stuff that we can see. So you can pick up a ping pong ball, you can play with it, you can mess around with it, but it's not just the ping pong ball that we're playing with, is it? If you waft your hand around like this, can you feel something? I'm guessing you can. You can feel the wind, you can feel the air around you, and we can use that air to do some cool stuff. especially if you've got something like a hairdryer. Now I'm going to try and hold this away from the microphone because it's going to sound horrendous, but if I do this just right, you can make a ping pong ball fly. I bet that sounded really bad. I'm sorry for your speakers, by the way. But try that one out at home. Remember to put it on the cool setting, not the hot air setting, because you'll melt the ping pong ball. But what I want you to think about with that is there's air moving and we can do stuff with it. And a great way to show that off, I'm going to put my box of materials to one side, is to think about what's inside these bottles. Okay, this one full of water, right? You can see like a normal drinking bottle. And the top one, that's empty, right? We've just said that it's not empty. Remember to look in the gaps. It's full of air. So if you were shouting at the screen then, well done, you're smarter than I am. It's not empty, it's full of air. Now what's going to happen when I turn this bottle upside down? So when I flip it over this way, is the water going to stay in this bottle? Put your hands up now if you think that. Is the water going to pour through into that bottle? Put your hands up now if you think that. So anyone who said it's going to pour through, you're absolutely right. If I flip it upside down, but it's slow and it's boring, isn't it? This is going to take forever. Does anyone know how to speed this up? What if I gave it a spin? That's a bit better, isn't it? So if you can spin the bottle, you can make a tornado. I'll show you that again. And all of a sudden, it will empty the bottle a lot faster. So there's air in one of the bottles, there's water in the other one, and they have to get past each other. So when I flip this round, give it a spin, I'm telling the water where to go around the outsides, I'm telling the air where to go through the middle. And so they can get past each other, and it lets things move, and it all works a bit better. So when we play with some of these materials, remember to look for what else is going on, what else is there that we can't see. And when we design our experiments, we're definitely going to have to do that. Now, if I said to you, find a material on your desk that was quite stretchy, what would you pick up? So have a look at your desk right now. Think about a stretchy material. What have you got there to play with? Probably some of you have got an elastic band. Maybe someone's got something else. Maybe you've got a hair bubble in at the moment. Maybe you could use that. Maybe some of you might have a spring. But I think the absolute classic example of something that you can stretch and play around with is obviously going to be a slinky, right? So I've got a slinky. I love slinkies. I have great fun with these. You can stretch them out. You can make them much longer than they were before. You can bounce them around. Have you ever got one to go down the stairs? Has anyone ever done that? Put your hands up now and show your teacher if you've ever got a slinky to go all the way down the stairs. And teachers, maybe you could let me know in the Q&A section how many of the kids in your class have managed to get a slinky to go down the stairs, because I can't do it. It just doesn't work. We tried it at work and it just wouldn't happen for me. So I can't get them to go down the stairs. But what I can do is another experiment where we drop a slinky. And if any of you have got a slinky and maybe a phone with a camera on it, you can try this out at home. So let's head over to the video and see what the experiment is. I think slinkies are a lot of fun. I like watching them bounce up and down. I like juggling them from one hand to another. But the really fun bit is when you drop a slinky. Because when we think about it, what are you expecting will actually happen when I let go of the top? Are you expecting the whole thing to fall? Are you expecting part of it to hover, float in midair? Well, no, of course not. You're not expecting things to hover. But I'm going to show you a video in a minute, and I want you to really keep a close eye on this bottom edge. And I want you to predict what's going to happen, because this is a spring. So don't forget, springs want to pop back to that shape they were in before. So is this bottom edge going to go up because it's being pulled back into shape like a spring? Is it going to fall down straight away because we've let go and gravity's pulling it? Or is it going to stay in exactly the same place? Now, I'm going to drop it for you and see if you can spot this. So let me just get that to stay still. Ready? Could you see that? My guess is no. It's a little slinky, it's quite close to the camera, wasn't exactly in slow-mo, was it? So we're going to need to think bigger, and I mean much bigger. So I have got a slinky about 3 times longer than this, and we're going to take it up on a crane, which goes to about the same height as 3 double-decker buses stacked on top of each other. So let's head over to the machine hall at WMG at the University of Warwick and have a look. Obviously, we can't send someone up the crane to drop the slinky, so we need a remote controlled device. We used a microbit, you might have used one of these in school, and we've programmed it to control a 3D printed robot claw. So the red lights count down, it turns green, and then the robot claw opens, and that will drop the slinky. So we attach that to the crane, attach the slinky to it, and then wound it up the full 10 odd meters of height. The orange light here tells us that it's ready to go, it's armed. I've highlighted it so you can try and see the slinky in the middle just there. And then we're going to see some red lights counting down at the top. We're waiting for that green light, and then the whole thing drops. Now it's pretty quick, so we'll try and see it from a different camera angle. Highlighted it here. The whole thing falls to the floor. What was your prediction? What did you guess was going to happen when it dropped? Let's see it in slow motion. The bottom of that slinky stays exactly where it is. The rest falls down to catch it up. Let's take a look at another shot. The red arrow is the top of the slinky, the blue is the bottom. And as it starts to fall, just about now, the red arrow falls while the blue arrow stays exactly in place. Now, here is a slow-mo shot to try and show it even more accurately. This is 16 times slower than real time, and it is currently falling, but the bottom stays put. Now, some of these shots, we are going to get some really beautiful detail as that bottom stays still and the rest falls around it. I put my phone really in harm's way here. This is just the slow-mo on pretty much any phone camera these days, but you have 16 times slow-mo, so that's 480 frames per second. You've got that green light at the top, so you know it's about to fall. You can just about see the top starting to move now, and the bottom is staying in place. It starts to spin around a little bit, but it isn't falling until the rest catches up, and then it all falls at once and smashes into your camera. So this is the last shot, just to show this in ultra slow-mo. So again, we're 16 times slower. You've got a green light at the top, and the whole thing is falling and unraveling, but the bottom stays where it is. That was honestly one of my most fun days at work I've ever had. I got to play with a crane, I got to play with slinkies, I got to drop them directly onto my phone. My poor phone, I know. But I did have a quick look at the comments just now, and I've seen that Arley School have actually got 17 people in their classroom who've managed to get slinkies to go all the way down the stairs. So there's 17 people in that classroom cleverer than I am. So well done, you guys. Now, you might have seen in that video that we had the slinky on a very fancy crane, a very fancy robot claw to hold it and drop it. But you could do that by hand. You could just have someone hold at the top of it and someone looking at the bottom and see if you can spot it with just your eyes. So it's an experiment that you can try at home. And it's all because that material is a spring. So it's quite stretchy, you can pull it apart, but it wants to pop back to that original shape. So the bottom is being pulled up. So when you drop it, the bottom's still being pulled up, so it doesn't fall until the top catches up and basically knocks it over. Now that claw that we used, that was 3D printed. So again, if you've used 3D printers or you've got them in your school, maybe let us know in those comments. If you've got one, there's lots of fun things that you can make with them. So I'm sure some of you have heard of 3D printers. You can make some things that seem impossible. So this is like a little cage and it's got a ball inside it. How do you think I got the ball in there? Because I can't get it back out. It's too big. It won't fit out any other way. It was all in one piece. It doesn't come apart or open. So how do you think this was made? Well, I've just told you it's a 3D printer, obviously. But what happens is that a robot comes along and it squirts plastics, melted plastic, and it squirts it in a pattern. And as it cools down, it gets hard and it builds the structure up all in one go. And we can make some really fancy things with these. So you might have seen something like a rubber duck. And I've got a little bit of echo. Is someone backstage not muted? Can I just check? Just before everyone gets really annoyed at a load of echo. Hopefully that has fixed it. So I've got a rubber duck here, and I 3D printed this in quite a clever way. So it's not just a normal rubber duck. If I pull it apart like that, it's actually a spring at the same time. So this is quite a wobbly rubber duck. It's quite stretchy and flexible. I can play with it. And it's just because I've designed it to be made in the same way as a spring, to have lots of gaps in between the material here. You can do the same thing with something like an apple. So there's a normal apple, and when I let go of the top, it bounces around, stretches out like a slinky. So again, if you've got a 3D printer in your school, you could look at making some of these things, and we can change the properties of the things that we build by copying something else. So copying the slinky makes the apple into a spring. But we don't just have to stop there. You know, that apple doesn't look very realistic. But what about this one? I mean, I'm tempted to take a bite out of this one, but it's probably a good thing that I don't, because it is rock hard. This is made of solid plastic. And again, we 3D printed this, but with a very fancy 3D printer. And we can make things that are really, really realistic. Now, you might be wondering, what is the point? What is the point of making plastic apples? And that is a very good question. We're talking about sustainability in this session. We're trying to save the planet. Real apples are healthy. They're good for you. They fill you up. Plastic apples, what's the point, right? Now, I'm going to show you something else that we've made on that same 3D printer, and I think that will convince you why this might be a good idea. This is a 3D printed finger. And we have got a very clever person at the University of Warwick who is designing and printing plastic fingers that are realistic, so you can bend them. They're squishy, they behave like real fingers. And he's actually even making some that have got bones and nerves and veins and arteries and things inside them. But I thought it was a bit too gruesome for this, so I haven't brought one of those. But why do you think somebody might want to make plastic pretend fingers that are ultra realistic? So I'm going to ask you that question. Why are we bothering to make pretend fingers? 10 seconds. Answer that question now. Off you go. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Time up. What did you think? What are you thinking about? Why might we want to make pretend fingers? I mean, one example for me is just that they're quite fun to play with, but that's not a very good reason to go and use very expensive equipment. We actually use these, we give them to surgeons and doctors to practice on. So if ever you have to have surgery on something like a finger, you want them to know what they're doing. Somebody's going to cut you open. I know, sorry, bit gruesome, but you want them to be well practiced. You want them to be an expert. You want them to know what they're looking for. And that is exactly why we need to give them something that they can practice on. So we print these fingers to be as realistic as we can. Now, I've showed you quite a few 3D printed things there. I've told you that we can change the way that these materials behave just by the way that we design them and the kind of materials that we choose and how we cut it and prepare it. But I'm going to ask you another question at this point. What I want you to do is think about wood. I'm sure you've all got something made of wood, maybe a pencil, or maybe your doors at home are made of wood. So you'll all have used or touched or played with some wood at some point, right? What words would you use to describe a piece of wood? I mean, what's the first thing that you think of? Is it stretchy? Is it squishy? Is it bendy? Is it strong? I mean, hopefully we're not saying flammable, because no, let's not go there. But you've got lots of different things that you can do with wood and just how you might describe it. I've got 3 pieces of wood here. So if I knock on them, they make a noise. So you can tell it's quite solid. Who thought wood was bendy? Put your hand up now if you think that wood is bendy. If you picked up a piece of wood like this, do you think you could bend it? What would happen if you did bend it? So hands up, if you think I bend this piece of wood, it will break. Okay, so people who don't have their hands up right now, well done. This piece of wood does not break when I bend it. So it's actually a really flexible piece of wood, and it's because I've used a laser to cut lots of little grooves and slots in this. So this piece of wood is so clever, I can actually stretch it and you can still see me through the piece of wood. So I bet none of you were thinking of see-through as a word for a piece of wood. It's stretchy, it's springy, it's bendy, it's flexible. And you could almost use this for, I don't know, a book binding or something like that. You could wrap a book up in it. And we can change the way that the wood behaves and have way too much fun playing with it just by how we prepare the materials. So you might want to think about that as well if ever you're doing an experiment or building something or making something in D&T. The way that you prepare your material changes how it might behave. So again, that piece of paper that we saw, that we folded it and it became a lot stronger. Now, wood, great for some things, but there's a lot of questions about it, and we might need to look at some fancier materials for some of the things that we use, like cars, right? Well, we've got a video that can show you why we don't make cars out of wood. If ever you're tasked with building something, maybe for D&T, wood is probably a good place to start. It's a cheap material, doesn't need complicated tools, you can grow it in your back garden, it's readily available, it's sustainable. Surely this is everything that we want. And it's great for building things like these model cars. But have you ever wondered why you don't see wooden passenger cars out on the road? If the material's so sustainable and so green we can grow it in the back garden, why not try and build cars out of it? The answer should be obvious to anyone who's ever got a splinter. Wood is really strong in its own way, but when it breaks into loads of really tiny fragments and splinters, and you can imagine how bad that would get in a car crash. Now, at WMG, we have a machine to test out materials being crushed and slammed together in collisions like this. And this video shows you just what happens when a natural material, plant-based material like wood, goes through one of these crashes. So if we're going to make a new material, if we're going to choose something that's going to be better than wood, what kind of fancy things could we design? What's the fanciest material you've ever heard of? Maybe you're thinking of something like carbon fibre. If ever you've watched F1 or any sport these days, you've probably seen some carbon fibre being used or talked about. And if you take a complicated scientific Lego set, something like this, where you get to play about with the materials and move molecules around and get all sciencey, you might come up with some really fancy materials too. Now, carbon fibre is great for some things. It's very light, it's very strong, it's made of these fibres that we stretch out and weave together. But again, when it breaks, boy does it break. It goes into millions of little fragments. And what we actually need if we want to absorb a crash and keep people inside a vehicle safe is a way to soak up the energy of the collision. We need to make sure that it doesn't just get sent out in billions of splinters. We need to make sure that there's something soft and nice to land on, something that can take that crash and keep people inside safe. So if ever you've folded a piece of paper like this, you might notice this is suddenly a bit springy. So this can soak up that force from me pinching it in the way that a normal piece of paper would just crumple up. It wouldn't bounce back. And the one material that can do this better than any other is metal. So again, let's have a drop to our video, and here you will see the metal just buckles and folds up. It doesn't shatter, it doesn't crack, it doesn't send fragments out everywhere, and that's why we build the complicated structural components of cars out of metal to build these crumple zones to keep us all safe. So if ever you're doing a challenge where you need to design a material or a product to keep something safe, like an egg, let's say, an egg drop challenge perhaps, you want to think about crumple zones. How can you soak up the energy and spread it out over a long time? Give it a go. So there you go, crumple zones. on all these pieces of paper. This is a paper spring that obviously you could make one of these, and it's really good at soaking up a collision. So if you ever are doing that experiment where you've got to keep something safe while you drop it without it cracking, do try and use these kinds of structures. So you've learned about that and how to make paper really strong so that it can support some weight. So if ever there's a bridge building competition or an egg drop challenge, there's no excuse now. You guys should be winning because you know how to paper engineer. You are paper engineers now, okay? But the other thing that I showed you in there was the really sciencey building block kit. And honestly, this is what science and engineering is sometimes, trying to make models to explain what's going on and what we're doing. And something I think is quite interesting. Have any of you ever seen the emoji of a football? Have you ever seen that pattern where it's a pentagon next to a hexagon? So 5 sides, 6 sides, 6 sides, 6 sides, 6 sides, 5 sides again. So those 5-sided shapes are always black and the rest of them are white. So if you see that emoji next time you're on a computer or on your phone, have a look for that. See if you've got that 5 sides, 6 sides thing. And notice it's exactly the same in science when we try and build a round molecule. So we have seen lots of different things with materials. We've destroyed quite a few, and unfortunately that is one of the best ways to test out how strong a material is. But again, you might be asking why? Why do we test these things until they break? Why do we destroy so many objects and items and things around us? And I can think of quite a few good examples of why we might want to choose exactly the right material for the right job. So if you think about something like a drinking straw, what material do you think a drinking straw should be made of? What is the ultimate material to make a straw out of? So I'll give you another 10 seconds. Maybe remember what your teacher said, whether it's hands up, shout out, turn to the person next to you, or write it down. What should a straw be made of? 10 seconds. Three, two, one. And if anyone noticed, I'm not very good at counting on my fingers there. But I think that one of the best materials to build a straw out of is actually a piece of metal. Now, you might have said plastic, you might have said paper, and this bit's even got a bit of silicone on the end. So if we get rid of that, it's just a piece of metal, it's just a metal tube. Hello. Now, if you said plastic, you might be saying that because it's really cheap, there's a lot of it, it's easy to make. Maybe some of you said paper. And again, paper is great because it's cheap and it's made from trees, so it's sustainable and we don't need much of it. It's quite easy to make. Metal, on the other hand, it's very hard, it's quite expensive, it's quite hard to make. You certainly couldn't just make one of these yourself at home. But what happens after I've finished my drink with a paper straw? It's going in the bin, isn't it? And when I use a plastic straw, I'm hoping that every one of you would recycle it. Hopefully you've all got recycling bins and you all use them. But if you don't, and that plastic straw goes in the bin, they can end up going anywhere. And unfortunately, I'm sure you've all seen pictures of plastic getting into the ocean. And imagine being a turtle and swimming around and thinking, ooh, food, num, 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 num. Ooh, food, num, 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 num. Ooh, what's that long white bit of food? And it's just a plastic straw and you've just swallowed a great big lump of plastic. We don't want that. And things like these metal straws are actually recyclable. They're reusable. So those are two things that we want to do to make sure we don't throw material away and waste stuff. So we want materials that are reusable, recyclable, and we just want to use less of them. So you don't need 2 straws, only use 1. Things like that. Now, that's how we might think about choosing the right material for the job. We might think about whether or not it's reusable. We might think about how safe it can keep us, like the crash structures in those cars we mentioned. We might think about whether it keeps us warm or how stretchy it is or how springy it is. But sooner or later, things break, don't they? Doesn't matter how hard you try to keep things nice, they get dented or bashed or broken or scratched or scraped. And what happens then? Do you have to throw it away? Can you repair it? Is it important that something can last for 10 years, or should you just get something that will only last a year? And I think it's quite important that we find out as early as possible how long these materials might last. So if you think about something like a paperclip, how strong is a paperclip? How long can you keep using the same paperclip for? And how many times could you bend it, straighten it all out before it would break? Now, this is another experiment that you can do in school. So if you've got a paperclip now, I'm going to show you what you can do with it. If you don't, you can do this after this video, after this session ends. But let's have a look at this video. So here's the experiment. We're going to take a regular paperclip, and what you're going to do is just try and bend it so that we can open it out into this shape, like an S, and then bend it back the same way until it looks like a paperclip again. And what we're going to do is just try and keep repeating that. So there's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and it's broken there. So you're just going to keep repeating it until your paperclip fails. We're going to test how many times you can bend these paperclips until they break. I wish I could say that no paperclips were harmed in the making of this video, but that is definitely not true. 100 paperclips were broken here to make this data set. You might want to think about doing this experiment and how you might plot the data. So here I've made a column chart, or a bar chart I suppose, flipped on its side, and you can see we get quite a few bends. So the number across the bottom is how many times I could bend it. So if it was up towards the right, then definitely these paperclips were quite strong. But most of them broke after just 2 bends, so quite weak. They failed quite fast. I tried it with a different pack of paperclips afterwards, so these brightly coloured ones. And actually, as you can see, most of them were further towards the right. So they took more bends before they broke. So that green line for the coloured paperclips, further to the right. So if ever we're in some kind of bizarre disaster movie where you're relying on a paperclip to save your life, you definitely want some of the coloured ones with the plastic around the outside, because they will last a lot longer. Now, I don't know what situation you're ever going to be in where a paperclip will save your life, but if ever you are, just remember that little tip. That extra bit of plastic around the outside keeps those paperclips stronger for longer. Now, remember, we do have a chance to ask some more questions. I've got about 5 minutes left of this show, so ask your teachers now if there's something that you really want to know, and they can type it in, and I will do my best to answer those questions. Now, if you remember back at the start, I put up lots of different words on the screen for different material properties. And how many of these have we thought about? Well, we've done strong, we've done strong materials, things like the metal that we looked at the start. We've looked at how hard a material is. That's whether or not you can scratch it. You've looked at stiffness with a piece of paper, and then when we folded it, it didn't bend. Well, obviously waterproofness is quite easy, isn't it? If you think about it, just pour some water on it, see if it goes through. We've looked at those drinking bottles, they're definitely waterproof. Can you see through something? So that piece of wood, when we stretched it, we could see through it. So if there's lots of gaps in something, you might be able to see through. What about colour? Let's have a quick look at colour. So if I ask you, what colour is this piece of wood? What do you think? Now, some people might struggle with this. I know I would, because I don't know whether this is blue or green. So let's have a quick think about that. Hands up if you think that this is blue. Okay, hands up if you think that this is green. Now, hands up if you think that this piece of wood is actually yellow. Now, I'm guessing there aren't many hands up, but if I take my hand away, there you go, we've got a yellow piece of wood. So just where my fingers were, that has turned yellow. And if I hold it up for a little while, you might see that that colour starts to fade and go back to blue. So we can change the colour of the material by warming it up, by heating it up. And I've got another little experiment for you. I've got my oven gloves here. I've got to remember to put them back in the kitchen after this, because otherwise dinner is going to be very painful. And if I hold this material for the same amount of time on each corner like this, so I'm trying to do a fair test, a fair experiment like you could do at home, which side do you think is going to be the most yellow? So if it goes yellow when it gets warm, is it going to be this side with my hand on it, or is it going to be this side with the oven glove on it? Hands up if you think the yellow side is the one with my hand. Hands up if you think the yellow side is the one with the oven glove. Okay, cool. Let's have a look. So the one where my hand has turned yellow. The one with the oven glove is still completely blue. So why do you think that is? Well, it's kind of the point of why the oven glove works, isn't it? It doesn't conduct the heat through. It keeps the heat in my hand and doesn't let the heat get through. Whereas my hand itself can take that heat straight onto the piece of wood and change its colour. And the other property that was up on that screen that you might be wondering about is magnetism. How do you tell if something is magnetic? Now, honestly, there's a very good explanation of magnetism. It all comes down to quantum mechanics. And what you need to do is think about Hund's rules and maximum multiplicity. Make sure you've got the most number of unpaired electrons in orbitals, all separated, pointed in the same direction, in a material with domain structures, with crystals that organize well. All of these electrons point in the same direction, and that influences the electromagnetic field. Does that cover it for everyone? No? Oh, okay. Well, to be honest with you, magnetism is one of those things that I think is a little bit magic, because we can take something and we can stick a magnet on it and it just stays there. And some materials are magnetic. So this can definitely is. If I picked up that piece of wood that I just used, that's not magnetic. And honestly, it's like magic. So some materials, anything that's got iron in it is going to be magnetic. It's quite a clever property. But the really clever thing about this, I'm going to try and hold this up to the camera so you can see, is that magnets can actually work through a material. So I've got a magnet on the top here, and I can move this backwards and forwards. And then I've drawn a butterfly on a piece of paper and stuck that to a nail, and the nail is on a piece of thread. So you might be able to just about see the piece of thread in there. And if I move the magnet backwards and forwards, the butterfly moves with it. So magnetism, that's why I think it's magic, is because it can go through a material like wood, and there aren't many other forces that can go through a material. I couldn't reach through that material and grab the butterfly. I couldn't move it in any other way. So when you've got a material that is made of metal, like iron, it can be magnetic. And it's a very, very complicated thing, but it's quite fun. Now, what I'm hoping we've done today is looked at all of these different properties of materials and given you the tools to test out and play with and tinker and experiment with the materials that make up our world. And if we all make those choices to be more sustainable and reuse, reduce, recycle, if we all make materials out of products that don't damage the environment, if we all have those right habits, and if all of you guys turn into engineers and start building these things and developing them and making that world greener, then I think we can look after those turtles, stop them eating plastic, and make sure this world is a nice one to live in. So go out there, test the experiments, explore the world, play with it, tinker, and find out the answers. Try out the experiments at home. I would like to give a massive thank you to my behind the scenes crew. We've got Lauren and Lucas and Margaret. Thank you all to your teachers for setting this up. Thank you for commenting in the questions and saying hi, and take care out there. Bye, everyone.